All right, let's get started and welcome back. It's good to see those of you who are here today. We've had a lot of fun the last couple of days looking at our class schedule. Working on lab number three has been a lot of fun for a lot of folks. I could definitely tell that. Um, it is definitely the case that as we've had some late night, last minute debugging sessions, it's been a lot less just syntax issues and a lot more conceptual issues, which is perfectly fine. And that's good. That's what I want to see happening. The other thing I want to see happening is people trying to kind of space out their progress a bit more. So it's not all last minute because it is just really hard to get this stuff done at the last minute when there's potentially unforeseen problems that can crop up over time. I mean that's okay. You all have many other classes you're taking and other things that are filling up your time. But as we see sort of the steady state for the schedule of this class, there is just a lot going on. We have our weekly quizzes and other assessments, weekly labs, weekly homework. It does all kind of add up, and so staying on top of what materials and what support I can provide for you is one way to be successful in this class. So today is the Wednesday, so it's time for quiz four. So everyone can go and open up Canvas, and I'll give you a minute to do that and navigate to that first quiz. Quiz number four listed there for today's date. I will just type the quiz code in the chat here so that people have it. And then, of course, as people um, come in late, we'll have to repeat it multiple times, and that's fine. But here it is, and this should take you about 5 minutes to do. So it isn't as instantly breezingly fast as a couple of the other ones that we have had. But this is closer to my idea of the type of questions I think I can ask on a Canvas in class exam like next Wednesday. So these would be two very mini subparts of an exam type question, but stuff we have certainly covered. So take about 5 minutes, go through these questions, and we'll all collect back here in five. We'll just take one more minute here to finish up and do your best on this. Okay. So as I've mentioned for these quizzes, some of the questions are for you and some of the questions are for me. So there's probably two different difficulty levels here in terms of this first question. Well, it's multiple choice. On the quiz, you can try it as many times as you want, and eventually you'll just get it right. We should have a pretty good feel for the kind of thing I was asking with regards to this. So there's very little MIPS code. We're just loading a single value from our integer array here. So the main question is really, do you recall sort of the syntax and the semantics of the load instruction? And that would lead you to know that something like this isn't really valid MIPS code. And then do we understand the byte addressable memory and the implications of that? And that would lead to which of those load word instructions is the valid one for our case here. Question two is probably only tricky because it's just sort of worded with a lot of things you have to read. It's here's valid C to MIPS translation for a branch using a branch equal in the example provided up here. If we instead wanted to compile a version that was branch not equal, which is um, this as the taken path and this as the not taken path, how does that change the code? And it changes the code in a very simple way here. Just the label we branch to changes, and then the order in which we have the add and the subtract instruction changes. So those are the two questions for you, and then the final question for me. This is a quiz that checks how well your TAs are doing more than anything else. So I'm very curious to know who has built some sort of rapport with their TAs, who just knows their TA's name for their lab sections. I did add some spurious TA names in here that you may or may not have gotten, and that's okay. I need something to keep, the humor going in this semester. So that is my attempt to provide a little bit of a flavor of what exam questions can look like next Wednesday. I'm guessing though it's going to be a mixture of those kind of sort of fill in the blank or multiple choice type questions, as well as ones where I can't seem to get it into that format very well, and it's just going to be more of okay, write the little block of code that does this, and then I have to manually grade those, and that's perfectly fine. Some maybe will feel more comfortable doing that. Others will feel much more comfortable with fill in the blank. It'll be a mixture of both, um, and that's fine. And I have, as I mentioned, I'm still kind of experimenting and figuring out what the right way to do that is. So it'll be a test with all of you with our first exam, and that's always fun. Um, so where we left off on Monday is we didn't get very far in terms of understanding the procedure call interface, but we were really looking at what was the new instruction that was required by it, and that was that jump and link instruction. And in that jump and link instruction, it acts otherwise quite a bit just like a jump instruction that we already covered to some extent, where you provide directly what the next program counter should be. It's not a PC relative address anymore. It's just here's what our next program counter's 28 bits should be, but we're also doing the and link operation. That is jump, change my program counter to this address represented by this label, and also store what the PC plus 4 value is for the current instruction so that I can get back. And it's storing it in a register that's dedicated to that purpose. That's where we left off on Monday, was looking at some of the architectural implications of having that RA register being that place where there's these and link class of instructions, and they are required to store that value in register 31. I think sometimes what can be the trickiest part of this, beyond the fact that the textbook says one thing, but it's very inconsistent with regards to this particular topic, It's just making sure we have a good handle on the terminology. The textbook likes to bring out recursive examples, which is fine and which is correct. But I think we'd be probably better served as opposed to doing a recursive example to start with, would just to start with a very simple example. And in that simple example, we can just assume there's some um, callee caller relationship. And apparently, this is the font I use for coding. So we have some function uh, called foo, and inside that function, we maybe have some variables. We should all use this for all of our coding practices here. And then at some point, we're taking some variable and we're calling some other function. Okay, and um, and then later on in the code, we have that other function, which itself we can add to that, which itself may in fact be calling something. So when we talk about this relationship of what is what, it's a relative relationship of what is a caller function and what is a callee function. In um, In this case, because we have function foo calling function bar, foo would be the caller function, and in the process of being called, bar would be the callee function. And that's just kind of, I think, just an awkward set of words that we're having to become a little bit more fluent with here. But that's caller versus callee. Um, But then, of course, bar itself could also be both, right? And that's where we have to just be very clear with what we're referring to, right? Bar itself could have its own, variables. I don't know, and bar itself could also be calling something where um, where we refer to bar as being the callee function in relation to its dependency with foo, because foo is the one calling it. But now, when bar itself is calling function baz here, then it's actually kind of both, right? It was already a callee function relative to foo, but now it's also the caller function, and now function baz is the callee function, right? And we can go and continue that as long as we want here. There could then be separately a function baz, which must take some input here, right? And then maybe that has some stack variables. It doesn't matter. We'll get to some of those details in a little bit. And that itself is going to be calling some other function. And then finally, eventually returning back. And it's all relative, right? So now that function baz was a caller in some context. It was a callee in some context because it was called by a function bar. But now it's also the caller relative to function quux. And as the old computer science joke goes, now we finally gotten to the crux of the matter. But that's the relative relation. Okay, it'll make sense later. Uh, that's the relative relationship, and that jump and link function is relative to that relationship as well. So when we refer to this jump and link instruction happening, there is no otherwise this like call function instruction in MIPS. Other ISAs do have something basically called a call instruction, but it's the same concept as our jump and link. That's just the terminology used by the MIPS inventors, by your textbook authors. So when we have this call here of from foo calling function bar, all that is really happening is there's some initial setup. So we have to make sure that's our variable y here. That y is being stored in a variable in a register dedicated for that purpose of storing argument values. So y is being put into A0, and then we're just having that jump and link instruction to whatever that label is, and it would usually just be the function name itself in a straightforward piece of code, where we jump and link now to that next function here. So it's just like a jump. And if this was not a function call, and if this was just some label in code, it would just be a regular jump. And then the other thing that winds up happening here, and it's kind of hidden in between the instructions or in the execution of this jump and link instruction is, all of these ultimately correspond to one or multiple instructions in our instruction memory, right? They have program counter values associated with them. And at some point, there's a PC value corresponding to the actual jump and link instruction itself, right? The actual location in instruction memory where that jump and link is actually found. And then in that jump and link instructions execution, the value of RA is then overwritten with this, whatever is next, whatever is PC plus 4. Again, the idea being that we store PC plus 4 there so that we can get back to where we want it to. And then when we actually then have a return at the end of that function that's being called, and we notice there's other extra calls that are happening in the meantime, but ultimately when we have the return that corresponds um, to that initial call here, so here's our function call, we wind up here, eventually there's a return corresponding to that call. It's going to return back to that PC plus 4 value that is stored in our RA, and we have an instruction that allows us to do that. It allows us to do other things as well, but specifically to return back to a program counter value that's stored in one particular register. It would be called jump register, and it has to be explicit here, but it would be jump register back to RA at the very end. So that's the basic pattern. There is some initial setup, and as we'll see, there can be quite a bit of setup required to make sure our registers and our other data is put where we need it to be. There's a jump and link instruction, which is both just a jump instruction as well as it's the and link functionality is this. And then the callee function's doing whatever it needs to do, including potentially calling other functions and setting up its own memory and things like that, and doing its own jump and link and things like that. And then eventually there is a return corresponding to that initial call, and that is executed via a jump register back to that PC plus 4 value that was stored in the RA register. We can already potentially see a problem if we're not a little bit careful here. Not to get into too much of what is potentially a headache here, but we have this call function or this jump and link instruction here, right? And in doing so, we've overwritten the RA. And at some point here, we also have a call or a jump and link um, instruction being executed when function bar itself becomes the caller and calls function baz. And that happens, right? That's a very natural thing where we have, if not even any recursion, we just have some depth of our function stack where function calls a function which calls another function. If you write object-oriented code, it's function, 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 50 times deep, right? But in this case, it's just 2. And so what would happen if we're not a little bit careful here, right, is we have a jump and link from foo calling bar. We would then also have a jump and link here to baz. And what would be the problem? Jump and link jumps to that location, which is what we want it to do. There's some setup of register A0 and things like that. That's fine as well. But what also happens when we do that jump and link, we also have that add link functionality, right? Where we've jumped here and we need to make sure we didn't write a return, but there is a return at some point. We store and overwrite the value of RA with that PC plus 4 value. Yes, exactly right. You would wind up overwriting that return address if we don't take care to ensure that there's a place where we can put that data storage that is needed on a function call by function call basis. Sounds like from some of the feedback we're getting a good feel for what's happening here. Let's talk about what that means in practice. So again, if you know jump and link and jump register, and if you can recall which one is caller and which one is callee, you're in pretty good shape to at least start with, I think. And so the next point is how do we actually deal with storing of that intermediate data? And this is for a lot of things, but certainly what if we need more than just what's there for the argument and return values? The data structure that almost all procedure call interfaces use is referred to as a stack. And you likely would have heard of the concept of stacks, in other contexts, just as a data structure. And it's exactly the same thing. A stack is a last in, first out queue, where the thing that is closest to your current pointer is the most recent thing that you put onto it. So we can talk a lot about pushing and popping onto the stack. I can't tell if people are joking or not, and that's fine. Refresh your memory what a stack does. But this is a stack, and it's a data structure in the same exact sense. It is a still a software managed data structure, but it's managed at a pretty low level because we're going to be using the same exact instructions we already have for reading and writing to memory to just keep track of the current location of our stack. So there's a lot of analogies, and okay, I can tell people are joking about that. That's fine. The idea being is it's a data structure that can grow dynamically, right? It's a place in data memory to put stuff. In this case, to put registers and other function local data we may need our function to be able to access. And it allows us to grow in a certain way so that one function's data isn't overwriting another function's data. So in MIPS, we have a dedicated register as part of the ABI, right? As part of the sort of de facto standard for writing code that plays nicely with other code. And that's referred to as the stack pointer. And that is just one of the general registers in our 32 registers that is used to keep track of where the stack currently is. It would have a starting location in memory, and then it would grow in one direction or the other. In the case of MIPS, it would grow backwards in our memory space to allow us to add content to it, to allocate memory for our particular function calls. And the term we use is for a particular function calls frame here. So we have a specific register, that's our SP, our stack pointer, and it is literally what it sounds like. It is a register that's holding a pointer to the stack. But pointers don't scare us anymore, right? We have our load word and we have our store word instructions, and they take a base address as one of the read registers it uses. And so we can use load words and store word instructions to access memory that's relative to that stack pointer. So those of you who did take your ComSci 228 and have studied some data structures, we know we have that push operation and our pop operation on the stack. And to push, if we assume that our memory is growing from high addresses back down to low addresses, pushing would then be decreasing the value of our stack pointer. In this case, if we wanted to push just a single word onto the stack and we would want to effectively allocate 4 more bytes on our stack, we would do so by subtracting 4 from the current stack pointer, so such that that stack pointer would then grow backwards in this direction. We would have a current value of our stack pointer. If we decide we need more data stored on that stack for whatever reason, we would then decrement our stack pointer. Right? Allocating of memory isn't like a magical physical thing that's happening, right? The memory itself is some physical thing, but our allocation or deallocation of memory is really just keeping track of pointers. And that's all that's happening here, whether it's an operating system doing it, whether it's our user code doing it, whether it's some system library doing it. In this case, it's at a pretty low level that we're keeping track of those pointers, but that's what it all really means to allocate memory. There's nothing physical happening here. There's no requirement that we, at least in this case, that we zero out or randomize the memory we've just allocated. Here, we're saying we want 4 more bytes to correspond to our current storage in the stack. We want to allocate 4 more bytes for that stack. We're just changing our stack pointer by a factor of 4. And likewise, if we decide we don't need a certain amount of memory anymore, where we want to now have the stack shrink by an equivalent amount, if pushing was adding more information to the stack and now popping is taking something from the stack, we could then update our stack pointer accordingly by adding a value of 4 to that stack pointer. So some ISAs do have explicitly a push and a pop instruction. And it makes sense because dealing with stacks is a very common thing that all architectures have to generally do if they support functions and procedures. For MIPS, though, we already have the instructions that do effectively what we would want it to do. So we could have had, it could exist a push instruction, but we know that we have a register dedicated for that purpose of keeping track of the current top of the stack. So this doesn't need to be its own instruction. It could, but it didn't need to be. It doesn't need to be. And instead we could replace that with an add immediate instruction. Presumably, when we're allocating data and we're putting data on the stack, it would be both an add immediate as well as a store word, a combination of instructions, right? We've allocated 4 more bytes on the stack because we want to actually put something there. But it could be one or the other. There's the allocation step and then there's the actual storage step. And likewise for the pop, generally, when we want to pop something from the stack, it's because we want to read that value and we're done with it. So it would be a load word followed by an updating of that pointer. But to actually do that popping operation, again, there's nothing physical happening there. We're just updating a pointer. We can do it with an add immediate instruction. And this is actually part of the ABI. And if you load it up in Mars, you'll see an example of that. Somebody has to determine, for code that's going to be executed on a system, what should the starting location of our instruction memory be? What should the starting value of our stack pointer be? And we do have to be aware of that when we're writing our own code to run in Mars, for example, or to run in any real system. Some of those things are kind of baked into the assumptions of working with this system. So your compiler or your OS need to be aware of that. When we're writing assembly code for Mars, uh, you could click the data memory layout tab, which will tell you exactly where things are supposed to be laid out in memory. You then are responsible for making sure your stack pointer starts at a reasonable location. Otherwise, you will get some somewhat annoying errors when you try this out. So I won't belabor the point. I'm reading some comments from people who have a decent feel of what's happening with this, but it's that growing of individual function call, procedure call frames of data as caller function A calls B. What happens in that process is we push some amount of data corresponding to B. Likewise, when then B, which was a callee, becomes a caller, is actually wanting to call C, we would then be pushing whatever data C needs to operate correctly onto the stack. When C finally returns, that would then be the popping operation. We no longer need that frame of data corresponding to procedure C. And likewise, B returns finally, ultimately, A returns, and your stack winds up empty. Um, so to actually do the pushing and the popping for MIPS, it is really just corresponding to, well, it depends on whether you actually want to read the data or not, or if you're just getting rid of the data. It really just corresponds to updating that stack pointer, which is just it's register 29. It's one of the 32 registers that you've all actually implemented already. So you have it, it's there for you. And so the actual push operation is just an add immediate. And so is the actual pop operation. So that this is to repeat the point I already mentioned. In MIPS, there is no explicit push and pop instruction. There could have been, but there isn't. So we're just using either loads and stores to put data on the stack and add immediate instructions to either allocate more data or remove or deallocate data from the stack. Um, Calling convention, our ABI requires a consistent way of interfacing across procedure calls in MIPS, the one that we use suggests very strongly that we have stacks that start at high addresses in memory and grow backwards in memory. The other little nuance here is that while the example showed just pushing and popping a single word on a stack at a time with an add immediate of 4 or -4, in practice we'll want to push the entire frame at a time or not, because a compiler should be able to determine at compile time for this function that you've written, um, and for the functions that we have here, a compiler should be able to determine exactly how much stack frame storage that particular function would need. It's nothing that's not known entirely at compile time. Um, some of this stuff isn't that obvious, but just for example, in this function baz, we do have some data storage that's local to that function. We can't actually put that in some global place because we don't necessarily know who's calling baz, how frequently baz is getting called. Is it going to be called by two functions at different times? Um, if it's not declared to be a static or any other sort of global storage here, this would then be stored on the stack relative to the frame for function baz. And the compiler can determine exactly that. It can say, well, um, this is an array of 100 ints. Each of those are 4 bytes each. Beyond just whatever other stack storage is needed for that function, we're going to allocate 400 bytes for the execution of that baz function. But for those other things we may need, for those other registers that are required as part of the procedure called convention and MIPS, the compiler or we as the compiler have to keep track of that stuff ourselves. So we will be emitting the code as we ourselves are the compiler this semester for putting things on the stack, allocating the right number of bytes in our stack pointer. This is one view of the MIPS process memory layout is what I would refer to this as, or just the data and text storage layout here. This is very comparable to what Mars presents to you as well. And there are some hard-coded values in there. At some point, somebody has to make a decision that, you know, your instructions start at this program counter address. Somebody has to make that decision, and that's part of that ABI for which this memory layout dictates a lot of those things. So we actually do know things such as what is our very first program counter going to need to be in our processor. That is, if we want a processor that's executing code from the standard compiler output for a MIPS compiler. So you will eventually, as you implement your program counter, have a reset condition that will actually reset it to this value versus resetting it to zeros. Likewise, there's um, allocated space for globals that we may have in our code. That's storage that's independent of any individual function, and so we have to have a place to put those. And that there's actually a global pointer specifically for that. That's yet another one of our 32 registers that if we want to access globals, it'll be relative to that global pointer. And then we have our range for our data that our code is otherwise using. That's our dynamic data. That's our heap as we're doing things like mallocs and new and things like that to dynamically generate data that we don't know at compile time how large it is potentially going to be. And then we have our data storage for our stack. And this is pretty common in most process memory layouts that you will see out there, where it doesn't necessarily matter which one grows from starting from low addresses to high addresses and vice versa. But it's extremely common to see, for example, the stack start at very high addresses, the heap start at very low addresses, and then have them sort of grow towards each other in memory. That is one kind of, we'll say, old school way of maximizing the amount of your data memory address space you can use before your stack and your heap start to collide with each other. Eventually they can, and you can certainly write C code right now that will crash at least the application because you've used too much stack. The compiler tends to have its own limits it enforces first before any real problem happens with data kind of corrupting itself. Um, but ultimately, there is a physical amount of memory and there's a limit to how much we can store. Having that stack start at high addresses and grow backwards, and the heap start at relatively low addresses and grow upwards, allows us allows us to not have to think about it too much. It allows us to assume that they're going to play nicely with each other, that they're going to allow to grow. And for both reasons, just like you have a malloc, you also would have a free call in RC. Likewise, as we add things to the stack, we're later going to be popping things from the stack. So they're not just always consecutively growing, they're going to be growing and then shrinking and then dynamically changing over time. This gives us the most amount of wiggle room in a pretty old school way of maintaining memory layout, just by allocating nice addresses and hoping that they don't run into each other. So the question that's coming for people who have to take a phone call and aren't here is, what is actually put on the stack frame? Here is the part that I don't think the textbook does that great of a job with. But for all the questions that we will get this semester, it'll be in the next 2 weeks primarily of, is my stack frame correct? Am I doing this exactly correct? The book says this one thing, but you in class on that Wednesday said something else. Ultimately, um, these issues are not as important as the ISA and the microarchitectural issues that we've been exploring in this class. Um, the concept's important. Understanding that a stack is there and it's a nice way to deal with local memory storage and keeping track of our registers from one function call to the other. That big picture concept, I think, is pretty important. I should be able to ask in a week or in few weeks, what is a stack? Why is it necessary? And I would expect you to be able to answer that. I should be able to ask you, what is the stack pointer? What is the point of a stack pointer? And you should be able to answer that. I will not ask you because I don't think the book does that good of a job with it, and maybe I'm not either. for this function, does the return address go before the saved arguments or does it go after the saved arguments? To be honest, it's not really that clear. And I think it's not really that clear because it's really not that important, right? Your own procedure frame has to follow certain conventions to make sure your code doesn't corrupt someone else's code. But within your own code, you do have a lot of flexibility with how you lay things out. So we'll call this the lecture slide version of what is on the frame, that frame of data, those bytes of data that are local to that particular function. Um, and somebody already asked, we have that issue that we pointed out with the multiple callee issue where jump and link to bar followed by jump and link to baz register RA gets overwritten. That seems very bad. Well, there's a number of registers where we then dedicate to being saved, to being registers that are going to be stored as part of this stack management scheme that is followed by all the functions that are going to play nicely with each other. And that's what's going to be stored on there. Um, Values that are dedicated to being saved that just by the ABI, we say for this registers, if we're going to use them, we need to make sure that we actually store them on the stack itself so that they're there for us. We can then pop them back off and get the previous value so we don't actually wind up corrupting our memory. So things like any saved arguments. So if a function's calling another function and we have the A0 through A4 registers, if we want to modify those, we should be pushing those on the stack. If we are going to be calling another function ourselves, we need to then store the return address on the stack itself. So to answer the question of how do we avoid this issue with the caller to callee with RA getting obliterated, that is the answer. This function bar would need to be the one, assuming they're all following the procedure call spec here. Bar would be the one that has to realize that I am overwriting, amongst other things, I am overwriting the RA register when I myself call jump and link baz. That is a callee save register. I need to be responsible for putting that on my stack frame. And then before I actually do that jump register back into RA, I need to be responsible to make sure that I've actually restored the value of that register and any other registers that are put into this general bucket, this category of callee save registers. RA is the most obvious example because we can see what's happening here. So at some point, whether it's the very first thing the function does, whether it's done immediately before the jump and link, there is no unanimity on that point. But at some point before that jump and link gets called, we need to play with the stack and we need to push at the very least that RA value on the stack. Otherwise, it does get obliterated and we never get back to that caller function. So that is where we would store any of those registers that we need to make sure don't get obliterated across the calling of our function. And that's also in the stack frame is where we're going to put our local storage. So that int a of 100 array that we had there, that's what we would put there. We would put 400 bytes on the stack. What we actually do with them really depends on what the function itself is doing. It's not a slow operation, right? It's not, we've allocated 400 bytes. That's going to take a very long, amount of time to do so. It's just incrementing our pointers. So allocating 4 bytes on the stack takes the same amount of time as allocating 400 bytes on the stack. Likewise, I could imagine a compiler that cares quite a bit about making sure our stack is as slim as possible, uses as few bytes as possible. When you are writing your code, and you're going to get this to work both in Mars on the simulator as well as on your own model sim VHDL implementation of your MIPS processor, it is perfectly okay to allocate more stack frame space than you need. It's much harder to debug having too little stack space than it is to allocate to debug having too much stack space. You'll just wind up with bytes that you're not using, and that's perfectly okay. So I'm seeing a couple questions here. Let's pause for a moment. Let's make sure everyone's. So yes, so in MIPS, ultimately this is true in all of our ISAs, but in MIPS we're doing stack bookkeeping ourselves. And we're doing it without any special instructions for stack bookkeeping. All of this allocation is literally just changing our stack pointer. So that's an add immediate. And putting things onto the stack, like copying the RA value onto the stack when we need it, that's a store word instruction. So you will see at both the beginning and generally at the end of all of the functions that are being generated from MIPS or that you yourself are writing, that stack maintenance or stack bookkeeping code is there. And almost all architectures that I'm aware of, and certainly for MIPS, the stack is not a physical thing, right? The stack is just a data structure in the same sense that it's a ComSci 228 data structure. It is just a region of memory that we say start at this location, and as your code is executing, grow it by frame as need be, push and pop things onto the stack as you need them. It's just an extra location in memory for us to do our loads and our stores. Yep. So that's what it would be doing. So the other question was, where does the RA go when we know we are overriding it ourselves, that this function is overriding RA for its own purposes? It needs to make sure this is why it's not part of the ISA though. There's nothing physical enforcing that function bar do this, right? There is no physical interface here. Right? These are just instructions that are already existing. But if we don't put it on the stack, if we don't push that RA onto the stack before we call jump and link, the code's just gonna be wrong, right? I mean, either if this is all code that you have written, it's just not gonna work, and so we want to avoid that if possible. And if this is a function that you're writing that someone else is going to be calling, because this is part of a library or part of some API or something, then your code's not going to play nicely with the rest of the code in the system, right? Someone's going to call your function, and it's never going to return back because the RA would have gotten obliterated in the process. Okay. So that's why we refer to this as sort of this software quasi standard. Certainly, a compiler is going to follow it. Your operating system is going to enforce some aspect of that. But there's really outside of the and link physically overriding a particular register in MIPS. Outside of that, there's really nothing architectural happening here. We can't tell as we're debugging our processor that we're dealing with a stack. The only thing we'd be looking out for is things like, well, I'm seeing register 29 getting overwritten quite a bit and it being used as loads and stores. Looks like some stack code is running right here. We're doing stuff with the stack. But otherwise, it doesn't look any different from any other add immediates, loads, and stores in our code. It's just by convention using a register that is dedicated for that purpose. The textbook also talks a decent amount about the frame pointer as well. Um, and I'll mention it here. If the stack pointer itself, SP, points to the last element in the stack, there is some convenience value of having a separate register that in fact points to the first value in that stack frame. And that's what the frame pointer, I believe it's register 28. I may even have that wrong, but it's a separate register in our 32 registers here that is pointing to that very first word in a particular procedure's frame. A common question is, do we need the frame pointer? And the answer is always no. It's a software programmer convenience issue. The argument as it goes is that the stack is potentially growing and shrinking dynamically in my function as I'm potentially calling other functions, right? In the code example we have here, there is no if about it. We're always calling these functions, but you could imagine I'm optionally calling this function or I'm calling this other function. And so the stack frame itself could have some branching associated with it, whether or not we grow the stack or not in a particular way. So for that reason, the stack frame itself, as I've executing my code, is changing. It is considered as assembly programmer convenience to instead have a frame pointer that doesn't change dynamically through the execution of your code. Relative to your function, the frame pointer is always pointing to the very first word of the frame. What the last word of your frame is changing potentially dynamically as your code is executing. So it's a software convenience issue. Well, that's from a day in which we were doing all of our development as much as possible via just assembly programming. And in this course, you're doing that as well again, but compilers don't really need the convenience factors. Compilers can keep track of that. That's what they're very good at, keeping track of pointers and things like that, and they're not going to get confused halfway through, compiling the code for your C code down to MIPS. So what you will tend to see is, the book will talk about the frame pointer. I may mention it once or twice again as we go in the future. But if you actually go to your compiler for MIPS and check out the results, it's very commonly just going to not have a frame pointer at all because it's not needed. It's just there to have another pointer that is static for the execution of my entire function, no matter how many other functions I call. And that can make addressing things on the stack relative to this register a little bit cleaner looking code and a little bit easier to keep track of than accessing things relative to this pointer that we have here. That's fine. If the question becomes, do I need to use a frame pointer? The answer is no. If the question is, this textbook says use a frame pointer, question says use a frame pointer, then use the frame pointer there. It's not strictly needed. I'm not sure if I could have confused that any more than I already did. But we're finally at a point where all of those labels for the various registers, now we can actually assign meaning for all of them. There's a couple missing here, but this is enough of them to get us started. So we already knew the zero register. That's something we're pretty familiar with, I think. That's ISA dictated functionality. Likewise, the RA register, that's relatively new to us, but now we do know that this is something that the ISA says register 31's got special functionality of those 32 registers, 0 and 31. Easy enough to remember. There's two. They're on the opposite ends. And the rest of these registers, we're still missing a couple here, but the rest of these registers um, have functionality that's all related to the procedure call standard way of doing things. So V0 and V1 are registers that are not physically dedicated, but logically dedicated to storing the results of function calls. A0 through A3 are for our arguments. We have our global pointers, which none of these examples are using globals, but once you have something that's just in global memory, you'll use that pointer instead of any of the others. And then our SP and our FP for our top of the stack frame and the bottom of that particular stack frame. Just pointers for us to keep track of that data structure. And the remainder of these are these T0s and T0 through T9 in this case, and S0 through S7. And we had been using them pretty interchangeably all semester. Sometimes we've used the S1s as our registers that are base addresses in memory, but there was no reason for that. It was just one way of keeping track of what registers I was using. Those names also then have some meaning in the procedure call interface. T stands for temporary register, and S corresponds to a saved register. And saved is just in the context of this procedure call interface where any register can potentially be saved. But the procedure call interface, the ABI for writing MIPS code that will play nicely with other MIPS code, specifies beyond just the ones that we know we would have to save for our code not to break, like the RA register, the stack pointer itself we have to be careful with. But then it also dedicates that, if you are going to be updating and modifying any of those saved registers, and again, that's S0 through S7 here, you as the function, even the caller function, have to push those onto the stack. Don't break those. Have those have the same state after you're done as they had before you started. And that's all that means. It's kind of an arbitrary thing versus if your code requires some temporary registers, as all of our code does, and we don't need too many of them, we can start off by using those T0 through T9 groupings of registers, and we just overwrite them as we please. If we want to save them ourselves, we can always do that. You can always push more things onto the stack. Those are the difference between, saved or preserved and not preserved. The other way of thinking about it is you could save any of those, but whose responsibility is it to save those registers? We differentiate between the callee saved and potentially the caller saved registers. So if your code is updating S0, because you want to use S0, you ran out of T0 through T9, you need effectively a T10 register, fine, you use S0, you need to push it on the stack first, and you need to pop it when you're done, so that the function that called you can have some guarantees that that value hasn't changed, even though there was a function call in the meantime. And likewise, if you have a value in S0 and then you have a function call, go back to this example that we have here, right? We have some variable z2 in this function bar. If we wanted to use z2 both before and after that call to Baz, then we would want to put it into a saved register, into S0 or S1 through S7. We're not required to. If we put it in a temporary register and we wanted to use it before and after the function call to Baz here, we could put it in a temporary register, but for our code to be correct, we would have to be responsible for actually pushing it on the stack and restoring it from the stack ourselves. But for S0, we have a guarantee that it'll have the same value before the function call and after the function call. Either way, we're pushing something on the stack. It doesn't happen via some magical mechanism. Either way, there's some enforcement that we have in place that says if you're updating an S register, got to make sure it's on the stack. Because this is both a caller and a callee function. That's why that terminology can be a little confusing in terms of, callee saved versus caller saved. For so many of these examples, the function is both a caller and a callee. It's just relative, right? Another way to think of it, and I think it makes more sense, is the preserved versus the not preserved register values. If my code in my function is updating any of these, I had better push it onto the stack. Let's leave things here for today. I think that was suitably complicated today. We'll continue on this example on Friday, and we'll walk through some textbook examples of what the assembly code can look like for doing this. But I do want to emphasize one more time that the nitty gritty details of exactly how many bytes our stack frame should be, the exact bookkeeping code for do we do add immediate first and then load word, or do we do load word first and add immediate? Those don't really matter so much. The big picture is that, having the stack frame allows us to have code that kind of plays nicely with each other. Big picture is use of the RA register. And then I would say also the big picture is the use of the stack pointer as a pointer into this data structure that allows these data frames to grow and shrink dynamically over time. The exact detail of is register V0 a preserved or a not preserved register? It's hard for me to care that much about that, and I don't want you to care that much about that. There is a section in the textbook that does go over that in some detail. It's also just not very consistent with what typical compilers will also generate for MIP. So let's pick this up right here on Friday. We'll try to do a fun example as well on Friday to kind of tie it all together at the end. Otherwise, good luck continuing on your labs and your homework due on Friday, and I'll see everyone then. Thanks.